Albert Einstein's discomfort with quantum physics was not born out of ignorance or conservatism, but rather from a profound philosophical unease with the nature of reality it implied. While he played a pivotal role in its early development, introducing the concept of light quanta and laying the groundwork for quantum theory itself, he became one of its most thoughtful critics. For Einstein, the probabilistic nature of quantum mechanics was not just counterintuitive, it was incomplete. He believed the universe operated under laws that were fundamentally deterministic, not governed by chance. To him, randomness signified a lack of understanding rather than a fundamental truth. What troubled Einstein most was the idea that particles could exist in superpositions, being in multiple states at once, and only take on definite properties when measured. This wasn't just strange, it was deeply unsettling to someone who believed in an objective reality independent of observation. His famous quote, "God does not play dice with the universe," was not a rejection of quantum theory's accuracy, but a cry against its philosophical implications. The notion that the act of measurement could collapse a wave function and determine a particle's state was, for Einstein, more magic than physics. He engaged in decades-long debates with Niels Bohr, a leading defender of the Copenhagen interpretation, which embraced uncertainty and observer dependence as core features of nature. Einstein could not accept that nature had no reality until observed. He suspected that quantum mechanics, though incredibly successful in predictions, was a statistical approximation of a deeper, hidden reality governed by variables not yet discovered. These hidden variables would restore determinism and objective causality, pillars of classical physics. His EPR paradox, developed with Podolsky and Rosen, was meant to show that quantum mechanics allowed for spooky action at a distance, the instant change in the state of one particle when its entangled partner was measured, even if they were light-years apart. This seemed to violate locality and suggested either faster-than-light communication or a breakdown in the concept of separable objects. Einstein hoped this would expose quantum mechanics as incomplete and spark the development of a more complete theory. But experiments decades later, such as those by Alain Aspect, seem to confirm that entanglement is not only real but inescapable. The universe, it appears, does allow for non-local correlations that defy classical logic. And yet, Einstein's concerns continue to resonate. His challenge pushed physicists to clarify the foundations of quantum theory and fueled the birth of quantum information science, including quantum cryptography and computing. Far from being a reactionary, Einstein was a radical idealist. He demanded that science not only predict but explain. He feared not the math of quantum theory, but its philosophical implications, what it said about reality, knowledge, and the limits of human understanding. He wasn't afraid of quantum mechanics because it was wrong, but because it might be right in a way that shattered his vision of a coherent, knowable cosmos. Einstein's reluctance to embrace the probabilistic framework of quantum mechanics reveals something deeper, a conflict between two worldviews. On one side stood the classical ideal of a universe governed by continuous fields and deterministic equations, an elegant tapestry woven by cause and effect. On the other was a realm where particles could tunnel through barriers, appear to influence each other instantaneously across vast distances, and refuse to have properties until measured. To Einstein, this was not just a new chapter in physics, it was a rupture in the logical fabric of nature. His dream was a unified field theory, a single framework that would elegantly combine gravity, electromagnetism, and quantum behavior. Quantum mechanics, in its standard form, was too fragmented, too discontinuous, and too reliant on chance. He compared it to a beautiful clock that tells time with astonishing accuracy, but whose gears are hidden behind a veil of mystery. For Einstein, science was not only about prediction, but about understanding why the universe behaves the way it does at every level. A theory that could only offer probabilities, no matter how precise, was not a final answer. The irony, of course, is that the very features Einstein found troubling, entanglement, non-locality, uncertainty, are now the foundations of emerging quantum technologies. Quantum computers, for example, rely precisely on superposition and entanglement to perform calculations beyond the reach of classical machines. Einstein helped open the door to this revolution, yet he would likely have found its implications philosophically troubling to the end. Even today, his critique of quantum mechanics continues to inspire alternative formulations. Pilot wave theory, objective collapse models, and various interpretations of quantum mechanics all grapple with the tension Einstein exposed. Though mainstream physics has largely accepted the standard interpretation, the desire for a deeper, deterministic underpinning still echoes through the work of many physicists and philosophers. Einstein's fear was not of science, but of meaninglessness, of a world in which reality vanishes the moment we look away. He believed that physics should describe the universe as it is, not merely as it appears when we measure it. His insistence on realism, on a world that exists independently of the observer, remains a powerful philosophical stance. He imagined a cosmos where the moon is there whether or not we are looking at it, where causes lead to effects, and where truth is not bound by perspective. His struggle with quantum mechanics was not a rejection of progress, but a refusal to settle for a fragmented view of reality. He was not content with answers that worked, he wanted answers that made sense. And in that pursuit, his fear of quantum physics was not fear at all, but a passionate demand for coherence in the face of chaos. Einstein's unease with quantum mechanics was rooted in its foundational divergence from the deterministic framework of classical physics, a framework grounded in differential equations, conservation laws, and local causality. In classical electrodynamics and general relativity, every effect has a traceable cause, encoded in continuous functions over spacetime. Quantum theory, however, breaks this continuity. The Schrödinger equation evolves deterministically, yes, but only until an observation occurs. At that point, the wave function undergoes a non-deterministic, non-unitary collapse, a process not described by the equation itself. This asymmetry deeply troubled Einstein. He viewed the measurement problem, the fact that quantum mechanics cannot explain when and how a wave function collapses, as a sign of theoretical incompleteness. He sought a more fundamental theory, possibly one involving hidden variables, that would account for the apparent randomness of quantum outcomes while restoring a causal structure. Moreover, Einstein objected to the statistical interpretation of the wave function, as championed by Born and Bohr. According to the Copenhagen interpretation, the wave function is a tool for calculating probabilities, not a direct representation of physical reality. But Einstein insisted that physical theories should describe real states of affairs in the world. If the wave function merely encoded information about our knowledge or predictions, then physics had surrendered its claim to describe the world as it is, not just as we perceive it. One of Einstein's most technically profound challenges to quantum mechanics came in the form of the EPR paradox. He and his colleagues Podolsky and Rosen constructed a thought experiment using a pair of particles in an entangled state. According to quantum mechanics, measuring the position or momentum of one particle instantly determines the corresponding property of the other, even if they are separated by vast distances. This seemed to imply supraluminal influence, violating the principle of locality embedded in special relativity. Einstein believed this paradox demonstrated that quantum mechanics was an incomplete theory, that some elements of reality were missing. He imagined that particles carried hidden variables determining their behavior, and that the spooky correlations predicted by entanglement were simply a result of shared hidden causes, not instantaneous action at a distance. However, in the 1960s, physicist John Bell formulated what is now known as Bell's theorem, which showed that any hidden variable theory that respects both locality and realism cannot reproduce all the predictions of quantum mechanics. Subsequent experiments, starting with those by Alain Aspect in the 1980s, violated Bell's inequalities, confirming that quantum entanglement cannot be explained by any local hidden variable theory. This doesn't mean Einstein was wrong in his criticisms, it means that the universe truly behaves in a way that defies classical expectations. Bell himself credited Einstein's insistence on philosophical clarity as the driving force behind his breakthrough. Einstein's preference for continuous field theories, like general relativity, was not arbitrary. In his unified field theory efforts, he sought equations that would reduce to both Maxwell's and Einstein's field equations under certain conditions, incorporating gravitation and electromagnetism into a single geometrical framework. He hoped that quantum behavior would emerge from such a theory in the same way thermodynamics emerges from statistical mechanics, as an approximation of deeper, deterministic microphysics. But quantum mechanics resisted this approach. Quantum field theory, the synthesis of quantum mechanics and special relativity, treats particles as excitations of underlying fields, yet still embraces the probabilistic essence of quantum behavior. In QFT, interactions are described using operators in Hilbert space and path integrals over all possible histories, not deterministic trajectories. Virtual particles, vacuum fluctuations, and non-commuting observables further erode the classical concept of a sharply defined, observer-independent reality. This non-zero commutator means that the observables themselves are incompatible in a deep algebraic sense. For Einstein, who believed that physical reality should not depend on the observer's choice of what to measure, this was unacceptable. He viewed this not as a revelation of nature's fundamental nature, but as a symptom of an unfinished theory. And yet, the experimental triumphs of quantum theory are undeniable. From the precise predictions of quantum electrodynamics, QED, which match experiments to 12 decimal places, to the development of technologies like semiconductors, lasers, atomic clocks, and quantum cryptography, quantum mechanics is one of the most successful scientific theories ever constructed. Still, the foundational questions Einstein raised remain open in many ways. Interpretations like many worlds, objective collapse theories, relational quantum mechanics, and Cubism each attempt to resolve the paradoxes Einstein identified, but none have achieved universal acceptance. Even in modern quantum gravity research, such as string theory and loop quantum gravity, physicists seek a unifying framework that would satisfy some of Einstein's original instincts: background independence, determinism, and mathematical coherence. The irony is that in trying to complete the theory he mistrusted, we may be continuing Einstein's deepest vision after all. Einstein's resistance to quantum theory wasn't a denial of its mathematical power, it was a search for a deeper ontological foundation. He wanted more than accurate predictions, he wanted a theory that described what exists, not just what is observed. His philosophical realism was rooted in a belief that the universe has an objective structure, regardless of whether we are measuring it. One of the core conflicts between Einstein and quantum theory lies in the concept of non-locality. In classical physics and general relativity, interactions propagate through spacetime at finite speeds, constrained by the speed of light. But entanglement, confirmed experimentally, implies that the quantum state of one system can be correlated with another instantaneously, across vast distances. This violates Bell locality, a condition that forbids such instantaneous influence. To Einstein, this was deeply problematic, not because he doubted the empirical outcomes, but because it suggested that either, A, reality is not local, or, B, measurement outcomes are not determined prior to observation. Both possibilities conflicted with his deterministic and field-based worldview. In essence, Einstein was forced to choose between two uncomfortable positions: a reality without locality, or a locality without reality. Quantum field theory, QFT, adds another layer of complexity. Although it unifies quantum mechanics and special relativity, it does so by allowing fields to fluctuate even in the vacuum state. The vacuum is no longer empty, it seethes with virtual particles, zero-point energy, and vacuum polarization. In fact, observable effects like the Casimir effect arise purely from vacuum fluctuations, something that would seem absurd from a classical perspective. For Einstein, the idea that nothing could exert force was a paradox, an indication that our current models were effective, but not fundamental. Moreover, quantum theory challenges the very notion of identity and distinguishability. In systems of multiple identical particles, the symmetrization postulate dictates that particles are fundamentally indistinct. This leads to the existence of fermions and bosons, whose statistical behaviors, Fermi-Dirac and Bose-Einstein distributions, underlie all of modern condensed matter physics. Yet Einstein, who famously predicted the Bose-Einstein condensate, still grappled with the metaphysical implications: if particles lose identity, what does it mean for individuality in nature? At the core of Einstein's skepticism was the belief that quantum mechanics was a phenomenological shell around a more complete theory. He suspected that the probabilistic structure we observe was a projection of a hidden, deterministic reality we had yet to mathematically articulate. In his later years, he worked tirelessly on a unified field theory, trying to reconcile gravitation and electromagnetism without quantization, unsuccessfully, but with great influence on future theoretical physics. This longing for determinism wasn't nostalgia, it was a response to an unresolved issue in physics even today, the measurement problem. What constitutes a measurement? Why does a superposed quantum state seem to collapse into a definite outcome? Why does the formalism distinguish between microscopic systems, which evolve unitarily, and macroscopic observers, which collapse wave functions? Decoherence theory has addressed part of this by showing how interactions with the environment can cause quantum systems to appear classical, but it does not solve the ontological question of when and how a definite outcome occurs. Einstein feared that if we accepted quantum mechanics as final, we might abandon the pursuit of an intelligible, unified cosmos. In a universe ruled by probabilities, causality becomes a fragile concept and prediction replaces understanding. He didn't reject quantum mechanics out of stubbornness, but because he hoped for something even more elegant. And perhaps he was right to push. After all, some of the deepest modern efforts in theoretical physics, like the holographic principle, string theory, AD/CFT correspondence, and quantum gravity, are attempts to bridge the gap between quantum theory and general relativity. These theories suggest that spacetime itself may be emergent, that entanglement may weave the fabric of the cosmos, and that Einstein's geometric vision and quantum non-locality may both be aspects of a deeper principle yet to be formulated. In this light, Einstein's discomfort wasn't fear, it was foresight. A refusal to settle for contradictions, a demand for clarity, and a belief that behind the shadows of probability lies a more complete cosmic architecture waiting to be revealed. Einstein's pursuit of a deeper theory led him to challenge not only the mechanics of quantum systems, but the very logic that underpins them. In classical physics, the law of the excluded middle holds: a particle either is or is not at a location, has or does not have a given momentum. But quantum systems violate this classical logic. A particle may exist in a superposition, a state that is neither here nor there, but both at once, described by complex amplitudes that interfere like waves. Such phenomena defy any intuitive ontology rooted in classical categories. To Einstein, this was epistemologically unsatisfying. He envisioned a future physics that would restore ontological definiteness without sacrificing the empirical accuracy of quantum mechanics. He hoped this would come through hidden variable theories, such as those later developed by David Bohm. Bohmian mechanics, for example, restores determinism by postulating that particles have well-defined positions at all times, guided by a quantum potential derived from the wave function. Although Bohm's theory reproduces the predictions of quantum mechanics, it does so at the cost of non-locality, something Einstein could not accept, despite his desire for determinism. Yet quantum experiments continued to support the probabilistic, non-local predictions of standard quantum mechanics. The violation of Bell's inequalities, tested in increasingly precise and loophole-free experiments, shows that no local hidden variable theory can match the empirical data. These results don't mean that Einstein was wrong to question the foundations, rather, they mean that nature is stranger than any classical theory permits. The cosmos really does contain correlations that can't be explained by shared local causes, even though these correlations can't be used to send signals faster than light. But the conceptual shockwaves go even deeper. Quantum mechanics does not allow for the joint reality of certain properties, such as position and momentum, not because of technological limitations, but due to non-commutativity. Observables in quantum mechanics are represented by operators, and the order in which they're applied matters. This leads to Heisenberg's uncertainty relations, which are not statements about measurement and accuracy, but about the structure of reality at the quantum level. For Einstein, this uncertainty was unacceptable as a fundamental limit of nature. He saw it as a sign that our theory was incomplete, just as thermodynamic entropy hides the detailed behavior of molecules. But unlike in thermodynamics, no deeper microstructure has yet emerged from which quantum probabilities can be derived deterministically. There is no known, quantum molecular mechanics, beneath the uncertainty. The very act of entanglement, which Einstein derided as spökhaft spooky action at a distance, is now regarded not as an oddity, but as the essential feature of quantum theory. In fact, modern quantum information theory defines entanglement as a resource, just like energy. It's what enables quantum teleportation, superdense coding, and quantum key distribution. Some physicists even argue that entanglement is the fabric of spacetime itself, especially in the context of the AD/CFT correspondence, where gravitational geometry on one side of the duality emerges from quantum entanglement patterns on the other. These ideas push physics beyond Einstein's time, but also align with his vision of a unified and intelligible cosmos. If spacetime and gravity are emergent from deeper quantum principles, then perhaps the future of physics lies not in rejecting quantum mechanics, but in extending it toward a more comprehensive, geometrically meaningful theory that includes gravity and quantum information as dual aspects of a deeper symmetry. Einstein's resistance, then, wasn't a failure to adapt, it was a refusal to accept contradictions as final answers. His relentless pursuit of clarity, realism, and unity continues to drive theoretical inquiry. In this sense, quantum physics did not defeat Einstein, it ignited a fire he passed on to generations of physicists who continue to ask, what is reality? What is information? And can a theory describe the whole without sacrificing the parts? Einstein's philosophical stance placed him at odds not only with the probabilistic formalism of quantum mechanics but also with its indeterministic implications for causality. In a classical framework, the state of a system at one time fully determines its state at any future time through deterministic laws, Newtonian or relativistic. But in quantum mechanics, even knowing the wave function with perfect accuracy does not allow one to predict the outcome of an individual measurement. Only the probability distribution can be known. This bothered Einstein deeply because it meant that causality had become statistical. Events could occur without sufficient reason. A radioactive atom could decay now or a million years from now, with no underlying cause, just a probability per unit time. To Einstein, this was antithetical to the principle of sufficient reason, the philosophical belief that nothing happens without a cause. His opposition wasn't to probability as a tool, but to its elevation as a fundamental principle of nature. In his attempts to formulate a deterministic replacement, Einstein hoped to incorporate quantum effects into a continuous field theory. His final decades were spent developing a nonlinear generalization of general relativity, a unified field theory that would encode matter and electromagnetism geometrically, just as gravity was encoded in the curvature of spacetime. He believed that if particles could be modeled as stable field configurations, singularities or solitons in a nonlinear field, then quantum behavior might emerge from a deeper classical substratum. But quantum phenomena like wave function collapse, discrete energy levels, and quantum tunneling do not easily emerge from classical fields. Moreover, quantum mechanics inherently involves Hilbert space structures, unitary evolution, and non-commuting observables, mathematical concepts that have no natural analog in the differential geometry of general relativity. Einstein's field-based approach lacked the capacity to explain why, for example, electrons and atoms occupy quantized orbits or why photons interfere with themselves in a double-slit experiment. Still, he intuited that something must unify the smooth, continuous structure of spacetime with the discrete, probabilistic nature of quantum events. Today, this vision lives on in attempts to develop quantum gravity. String theory, for instance, replaces point particles with one-dimensional strings whose vibrational modes correspond to particles, uniting gravity and quantum mechanics within a single framework. Loop quantum gravity attempts a different approach, quantizing space itself into discrete loops, suggesting that spacetime is fundamentally granular at the Planck scale. Interestingly, both approaches respect certain elements of Einstein's dream: background independence, space is not a fixed stage, diffeomorphism invariance, physical laws don't depend on coordinate labels, and a unification of forces. But they also integrate deeply quantum concepts, superposition, uncertainty, entanglement, in ways that Einstein might still have found unsatisfying, or at least incomplete. Even modern developments in black hole thermodynamics and the holographic principle reveal tensions Einstein anticipated. The discovery that black holes have entropy, via Bekenstein and Hawking, and radiate like thermal objects implies that quantum information is somehow encoded on the event horizon's surface area. This hints at a radical restructuring of our understanding of spacetime and information, suggesting that the volume of a region is emergent from quantum degrees of freedom on its boundary. The ADS/CFT correspondence, one of the cornerstones of modern theoretical physics, shows that a gravitational theory in a bulk spacetime can be equivalent to a quantum field theory on its boundary, with no gravity at all. This kind of duality, where gravity and quantum mechanics are two descriptions of the same underlying phenomena, is exactly the kind of unity Einstein sought, though he did not have the mathematical or conceptual tools in his era to foresee it. And it shows that his deepest concern remains valid. Quantum mechanics may be astonishingly powerful, but it likely is not the final story. Einstein's disquiet was not about technical details, it was about coherence. He believed that nature should ultimately be describable by a logically complete, internally consistent, and ontologically meaningful theory. One in which all phenomena, from the orbits of planets to the collapse of wave functions, arise naturally from first principles. That dream remains one of the highest aspirations of physics today. Einstein's pursuit of a deeper understanding of reality reflected a rare kind of intellectual integrity. He was unwilling to accept a theory that merely worked if it lacked explanatory depth. For him, a satisfying physical theory had to be more than empirically adequate, it had to reveal the architecture of the universe. This conviction placed him in growing isolation as the quantum revolution advanced, but it also preserved a critical tension in the development of physics, the need to reconcile mathematical formalism with conceptual clarity. One of Einstein's most fundamental objections concerned the wave function's ontological status. In the Copenhagen interpretation, the wave function is not a physical object but a mathematical abstraction, a tool for predicting outcomes. But what, Einstein asked, does the wave function represent in the real world? If it's not real, then quantum theory seems to describe nothing but human knowledge or belief. If it is real, then how does it collapse instantly across space? Einstein suspected that both options were flawed. This dilemma is sharpened by Schrödinger's cat, a thought experiment that emerged from precisely the same discomfort. A cat placed in a quantum superposition of alive and dead is not just a metaphor, it's a profound critique of quantum mechanics as applied to macroscopic objects. If we accept the formalism literally, then not only atoms but cats, brains, and observers themselves can exist in superposed states. This threatens the classical notion of definite states and challenges the very possibility of an observer-independent world. Modern interpretations attempt to address this. The many worlds interpretation asserts that all outcomes occur, each in its own branch of a vast, ever-splitting multiverse. In this view, there is no collapse, only branching. While this restores determinism and treats the wave function as real, it comes at the cost of a staggering metaphysical commitment, a literally infinite number of parallel realities. Would Einstein have accepted such an interpretation? Unlikely. He sought simplification, not proliferation. Other approaches, like objective collapse theories, e.g., GRW or Penrose's gravity-based models, modify quantum mechanics itself to introduce spontaneous collapses that do not require observation. These theories restore a kind of realism and attempt to explain why macroscopic objects do not exhibit quantum weirdness. However, they require new constants of nature and have yet to produce definitive experimental predictions that differ from standard quantum mechanics. Meanwhile, quantum information theory has taken a radically different approach. Instead of treating the wave function as a description of reality, it treats it as a catalog of information, essentially a communication protocol between observers. This perspective, known as QBism, quantum Bayesianism, sidesteps ontological questions by asserting that quantum mechanics is not about reality at all, but about agents updating beliefs. To Einstein, who believed passionately in the mind-independent existence of the universe, this would have seemed like a retreat from realism into subjectivity. And yet, even as the field has diversified into dozens of interpretations, Einstein's original challenge, that quantum mechanics lacks a clear picture of reality, remains unresolved. Each solution brings trade-offs. Restoring determinism costs locality. Preserving locality demands abandoning realism. Maintaining both forces us into non-classical logical structures, or into abandoning the notion of a single, actualized world. These tensions grow even sharper at the intersection of quantum mechanics and gravity. Black holes, for instance, encode some of the deepest paradoxes in modern physics. The black hole information paradox, whether information is lost when matter falls into a black hole, pits quantum unitarity against the classical geometry of spacetime. Hawking's original calculation suggested that information is lost forever, contradicting quantum mechanics. Later developments, including the holographic principle and firewall paradox, suggest that resolving this issue will require a radical revision of spacetime, information, or both. This is where Einstein's legacy is most palpable. He understood that any true theory of nature must unify the smooth geometry of gravity with the probabilistic events of the quantum world. It must explain how a particle's wave function evolves when spacetime itself becomes a quantum object, curved, foamy, uncertain. His own general theory of relativity, a triumph of determinism and geometry, has not yet been successfully reconciled with the indeterminism and linearity of quantum theory. Even now, in the most advanced frameworks, whether it's string theory's vibrating dimensions, loop quantum gravity's quantized space, or emergent spacetime models from entanglement, Einstein's fingerprints remain. The insistence on unity. The belief in a deep coherence beneath apparent contradiction. The refusal to accept paradox as explanation. He once said, "The most incomprehensible thing about the universe is that it is comprehensible." That belief, that the universe is, in principle, intelligible, was his guiding light. In resisting quantum mechanics as a final theory, Einstein was not denying its power, but asserting that our journey toward understanding is not yet complete. Einstein's legacy in this ongoing tension between quantum theory and classical intuition is not one of rejection, but of provocation. His critiques did not weaken quantum mechanics, they sharpened it. By insisting that quantum theory must either be completed or reinterpreted in a way that restores coherence, Einstein forced the physics community to ask questions that remain fundamental today. He refused to let mystery masquerade as understanding. Modern physics, in many ways, is still grappling with the problem Einstein posed: how can a theory that is so wildly successful in predicting outcomes be so conceptually opaque? In what sense is the wave function real? How can spacetime, so geometrically elegant in general relativity, coexist with the bizarre, non-local phenomena of quantum entanglement? And if gravity is geometric, and quantum fields are probabilistic, then what is the ontological status of a gravitational field in a quantum superposition? These are not esoteric puzzles, they lie at the heart of cutting-edge research in quantum cosmology, quantum gravity, and the foundations of information theory. In trying to answer them, physicists have begun to see that perhaps the path forward lies not in choosing between Einstein's realism and quantum mechanics' formalism, but in discovering a deeper theory that contains both as limiting cases. In fact, one of the most radical ideas to emerge from this search is that spacetime itself may not be fundamental. In certain approaches, like tensor networks, AD/CFT dualities, and emergent gravity theories, the smooth geometry of space and time arises from the entanglement structure of an underlying quantum system. That is, the distance between 2 points in spacetime may correspond not to a coordinate separation, but to the amount of entanglement between degrees of freedom in a quantum state. This perspective is strikingly alien to classical intuition, but it resonates with Einstein's ultimate desire, to reduce complexity to simplicity. Perhaps gravity and geometry emerge not from additional fields, but from the patterns of quantum information. Perhaps the field equations of general relativity are not written into the fabric of reality, but emerge as thermodynamic or entropic approximations of a more fundamental microphysics. In this way, Jacobson, Verland, and others have derived Einstein's equations from first principles using ideas from quantum information theory and thermodynamics. Such developments show that Einstein's dream of unity was not misplaced, it was ahead of its time. Though he did not believe in quantum mechanics as a complete description, he may have sensed that something deeper was buried beneath its probabilistic surface. His call for realism, causality, and completeness has evolved, not disappeared. Where once his contemporaries saw his critiques as outdated, many now recognize them as prophetic. Even in the context of quantum foundations, experiments are beginning to test the very structure of reality Einstein debated a century ago. Delayed choice experiments, quantum erasers, loophole-free Bell tests, and gravitationally induced entanglement proposals are all probing the boundaries between observation and existence, between information and ontology. These tests are not only experimental triumphs, they are empirical responses to the philosophical anxieties Einstein raised. One might even say that quantum theory has grown into its own contradictions, so much so that it now seeks to transcend itself. The more we learn about decoherence, quantum measurement, and entanglement entropy, the more we suspect that quantum mechanics, like Newtonian mechanics before it, is a special case of something vaster. Something that can unify the fabric of spacetime with the fabric of information. Einstein would not have feared this expansion, he would have demanded it. He believed that physics was a dialogue between mathematics and meaning, between symmetry and substance. And although he stood outside the mainstream of quantum interpretation, his voice still echoes within it. We now know that his challenges were not dead ends, they were signposts. The tension he exposed between locality and completeness, between determinism and probability, between geometry and algebra, is not a flaw in his vision but a map of the territory we have yet to explore. Physics has not yet answered Einstein's deepest question, is the universe fully knowable? But the very act of asking it, again and again, at deeper and deeper levels, is itself a kind of knowing. And in that sense, Einstein was not just a critic of quantum theory. He was its conscience. And so, in the grand arc of modern physics, Einstein's struggle with quantum mechanics was not a rejection of progress, but a refusal to accept fragmentation as truth. His discomfort was not with uncertainty itself, but with the idea that uncertainty might be all there is. He envisioned a universe where clarity and causality were not illusions, but clues, whispers of a deeper order just beyond our reach. Today, as we peer further into black holes, entangle photons across kilometers, and simulate universes on quantum processors, we stand in the shadow of his questions. We find that quantum theory, despite its unparalleled predictive success, remains haunted by the very mysteries Einstein illuminated. His insistence on unity, reality, and completeness continues to challenge us, not because he was behind his time, but because he was reaching beyond it. In the end, Einstein did not fear quantum physics. He feared that we might stop asking why.